All right, I really think the best way to solve for the activation energy is to make an Arrhenius plot and do some linear regression. But sometimes maybe we just have two data points, and so maybe we want to come up with a way to do it using a little bit of algebra. So let's go ahead and use our algebra skills to figure this out. Okay, so we should probably start with the Arrhenius equation. So k equals a, the pre-exponential factor, times by e to the minus activation energy over RT. And we're going to go ahead and we're going to take natural logarithms. And so natural log of k is equal to, well, the right-hand side's a product, so natural log of the first term plus natural log of the second term. And remember the second term here, we've got our anti-logarithm, and so when we log it, it vanishes and becomes minus EA over RT. And what we'll find is that it's often convenient to pull the temperature out. Let's say we've got two values. So at some temperature T1, we've got a rate constant K1, and a second set of conditions at some temperature T2, we've got a rate constant K2. Now we can put these together, and we can go ahead and we can take each term and add them up, or insert them into the equation. So log of K1 is equal to log of pre-exponential factor minus EA over R times by 1 over T1. And we could do the same thing for the second condition. So log K2 equals natural log of A minus the activation energy over R times by 1 over T2. What are we assuming here? Well, we're assuming the pre-exponential factor doesn't change with temperature. And that's actually probably a little bit naughty. It turns out that the pre-exponential factor has a slight, ever so slight change with temperature. But it turns out that it's overwhelmed by the Boltzmann factor. The e to the power part changes dramatically with temperature. A by itself might only change by a few percent over 5 degrees. So most of the time we can pretend that unless we've got a massive temperature change, A is exactly the same. The activation energy, that's the barrier height, and it doesn't change with temperature, but we know the hotter the temperature is, the easier it is to cross the barrier. So what can we do with these equations? We can go ahead, and if we're trying to find the activation energy, we can subtract these equations from each other. And so if we subtract them, the natural log A terms are going to disappear. And what do we have? We got the natural log of K1 minus the natural log of K2. And on the right-hand side, what do we have? Well, these terms have canceled out. And so we've got minus EA over R. And we're subtracting 1 and 2. And so we're going to have 1 over T1 minus 1 over T2 here. So I've just factored out the minus EA over R term. All right, properties of logs. We know that log of A over B is equal to log A minus log B. And so that means up here, where we've got the log of one thing minus the log of the other, we can rewrite that actually. We can recognize that that's just the natural log of K1 over K2. Okay, I don't think the right-hand side we can do too much cleaning up with. Maybe we can actually. So this minus sign here, we can distribute into here, and that gives us EA over R. And if we distribute it in, this minus becomes a plus. And so this becomes 1 over T2 positive, and then this plus here becomes a minus, and we can just write it in second place. So that's 1 over T1. And so this gives us a very common equation when we're trying to solve for the activation energy. If we're given all these unknowns, these two temperatures and these two rate constants, and we can look up the gas constant, we can solve for the activation energy. I'm not sure how necessary this next step is, and I think it's one of those things that if you've got a brain-dead calculator, or if you used a slide rule 50 years ago, you probably had to do it. But it is fairly common, and so I should probably show you why sometimes the equation above looks different. The term in square brackets, the 1 over t2 minus 1 over t1, 1 over t2 gives you a small number, 1 over t1 gives you a small number, and you're subtracting two small numbers one away from the other. And this often leads to giant calculator errors. And so one thing we can do here is we can rewrite it a little bit differently. So for instance, the 1 over t2 term, we can go ahead and we can multiply top and bottom by t1. And we can have a look at what this does here in a second. If we take the 1 over t1 term, we can choose to multiply it, top and bottom, by t2. So what's the point of doing all of this? Well, the point of doing all of this is that now we've got a common denominator. And so the bottom is t1, t2 in both cases. And we know with fractions, when we add or subtract them, we can just add the tops together as long as the denominator is exactly the same. So now we've got a common denominator. We can go ahead and rewrite this as t1 minus t2 over t1, t2. So this means that that term in square brackets then can be totally rewritten, and this is the form that sometimes you'll see. So log of the two rate constants equals the activation energy over the gas constant, and then we have T1 minus T2 over T1 times by T2. And that's quite often easier to calculate than the term above.